Well, good afternoon, everyone. Thank you for coming out. My name is Tom Landy. I'm the director of the McFarland Center for Religion, Ethics, and Culture here at the college. At its core, the McFarland Center seeks to strengthen the intellectual and moral life of the campus and community. We work in partnership with faculty, students, and visiting scholars to support research, teaching, and public inquiry on questions of meaning, morality, and mutual obligation, while also fostering a deeper understanding of religions and ethical traditions in global context. Through faculty seminars, research, fellowships, and collaborative initiatives and public programs, we aim to build an enduring scholarly community, one that connects individual work to larger institutional and global conversations. This afternoon's lecture brings that mission of conversation with one of the most consequential challenges of our time, understanding the science of climate change and the responsibilities that come with communicating scientific knowledge in the public sphere. Few areas of scientific inquiry have become as central to public life as climate science, and so paradoxical, accepted as incontrovertible in almost all of the scientific community, but rejected by so many other people in the public. Thus, we're especially pleased to welcome Ben Santer, one of the leading climate scientists of the past several decades. Over more than 30 years at the Lawrence Livermore National Laboratory, Dr. Santer conducted pioneering research on the detection of human influence on climate. His work brought together climate modeling and observational data to identify what scientists call the fingerprints of global warming, distinctive patterns in climate records that allow researchers to distinguish natural variability from the measurable effects of human activity on the Earth's atmosphere. He served as a lead author of the landmark 1995 assessment report of the Intergovernmental Panel on Climate Change. That report concluded for the first time that the balance of evidence suggested that a, quote, discernible human influence on global climate, a historic turning point in the scientific understanding of climate change. In recognition of his contributions to climate science, he was elected to the U.S. National Academy of Sciences in 2011. This afternoon, Dr. Santer will reflect on the scientific journey from that early finding to the much stronger conclusions reached today, and on what it has meant to communicate climate science in a public environment where scientific evidence is often challenged or contested. Today's event is co-sponsored with the Environmental Studies program, and I'm especially grateful to my colleague, Professor Keith Sider, for his leadership in bringing this important conversation to campus. So please join me in welcoming Ben Santer.
Thank you, Tom. Good afternoon. It's such an honor to be here. This picture is from a former colleague of mine at Lawrence Livermore National Lab, Céline Bonfils. She was actually at a conference in Colorado and during a hike saw this dried out or nearly dried out lake bed and put her handprint on the dried out lake bed. It was at a time that we were writing a paper together in Nature Climate Change about the effects of human-caused warming on drought. And this picture that Céline took with her iPhone made it to the cover of Nature Climate Change. The lesson from this story is it doesn't always have to be the most sophisticated graphics. Sometimes some thoughtful action can also be very meaningful and can reach people. A few brief words about myself. I'm a US citizen, but my folks moved to Germany, to Dortmund, in 1966 when I was 11 years old. And I went to a British Army school as the only American kid who couldn't play cricket, soccer, rugby, or all that other stuff. It was a very steep learning curve. And subsequently, I went to college in the UK and then eventually did a postdoc in Germany. My research, as Tom mentioned, is in climate fingerprinting, the use of pattern recognition methods to disentangle human and natural effects on climate. And my hobby is rock climbing, which I still do with my son, who you see here, at beautiful Pinnacles National Park, east of Santa Cruz. He has all the responsibility now. My job is just to follow him. So the baton of leadership has been transferred from father to son. As Tom mentioned, the Intergovernmental Panel on Climate Change, or IPCC, assesses the physical science of climate change, the likely impacts of climate change on things we care about, and possible measures for adapting to and mitigating the effects of climate change. The first report was published in 1990, and it essentially concluded that the jury is out in terms of whether there is or is not a human-caused climate change signal. 5 years later, the second IPCC report in 1995 came to a fundamentally different conclusion. The jury was in. And these 12 words are forever engraved on my memory because they occurred in the chapter that I was responsible for. The balance of evidence suggests a discernible human influence on global climate. It wasn't, eureka, there's water in the bathtub, we understand everything, but it was the first time that the international scientific community spoke with one voice and said, formally, we can identify a human-caused global warming signal. It's risen above the noise of natural climate variability. As I'll discuss later, that was an extraordinary event, scientifically and in my personal life. A lot of very powerful people and organizations and even countries didn't like that finding. It was bad for business. The next IPCC report came to a stronger conclusion regarding the reality of human effects on global climate. That's how science works. An independent group of scientists reanalyzed the evidence that we had looked back at in 1995 and said there is new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities. The fourth assessment report in 2007 introduced this likelihood language that warming was very likely due to the observed increase in greenhouse gases. In 2014, the likelihood language was ratcheted up still further, extremely likely, where that had a specific probabilistic meaning, greater than 99% probability that the statement was correct. And the most recent IPCC report in 2021 essentially ran out of space in terms of the likelihood language and used this extraordinary word, unequivocal. It is now unequivocal that human influence has warmed the atmosphere, ocean, and land. So this is the arc of history that's encapsulated in these 6 IPCC reports. Why? Why has there been this advance in scientific understanding? What factors enabled it? There were many. Please come in. There's space up here at the front. So I would argue that one of the factors that enabled this arc of history here and scientific understanding of the reality of human effects on climate was we had more climate models. In 2021, at the time of the 6th IPCC report, there are about 100 climate models from most countries in the world. Back in the 1990s, we only had half a dozen, roughly. These models are better, too. They're now, today, full models of the Earth system, not only the atmosphere and ocean, but also ocean biogeochemistry, the carbon cycle, the land surface, complex atmospheric chemistry. And we have a better understanding of the factors that influence climate, both human and natural, not only human-caused changes in greenhouse gases that arise from fossil fuel burning, but also particulate pollution, things like soot aerosols, natural changes in the sun and in volcanoes. That too has enabled the progress that I showed you. Back in the early 1990s, satellite-based records of global scale changes in Earth's climate were relatively short. They started in around 1979, so we had back then only a very, very short satellite record of changes in global temperature, moisture, and other things we care about. Now, those records are over 45 years long. Critically, one of the things that's happened too is that the entire community is analyzing the results from model simulations and observations. That wasn't the case back in the early 90s. Now we virtually have crowdsourcing of the analysis of model simulations through national and international programs that make simulation output and make satellite data available to the entire global scientific community. And from the comfort of your own office, you can interrogate these huge archives of observations, of model simulations, and do research with them. That's been transformational. We have things like the Earth System Grid Federation, a system for sharing not only model data and satellite data, but also analysis code for visualization and for statistical analysis. All of that has been huge. What I'm mostly going to talk about is this consilience. I think the progress that I showed you in scientific understanding of human effects on climate has been enabled by consilience between basic theory, modeling, data, and these pattern recognition methods, these so-called fingerprint methods. Consilience is a word that was made popular by the great biologist E.O. Wilson at Harvard, and it's the principle that evidence from independent, unrelated sources can converge on strong conclusions. And that's what I'll try and convince you of next, that we had theoretical understanding of how greenhouse gases work, how they trap heat. And in tandem with that theory, we had simple models back as far as the early 1900s that tried to encapsulate that theoretical understanding in models that could enable us to look at what happened to temperature when you increase CO2. We have data, as I mentioned, now from satellites, truly global understanding of changes in our planet's climate since the late 1970s. And we have these complex methods, now tools like AI as well, for trying to disentangle human and natural effects on climate. Theory, I'll start off with theory and early models. This gentleman is very famous in climate modeling, Suki Manabe. He wrote in 1967 a paper with his colleague Dick Weatherald from the Geophysical Fluid Dynamics Lab. And for this work, Professor Manabe won part of the 2021 Nobel Prize in Physics. What did Manabe and Weatherald do back in 1967? They used a very simple model, a so-called radiative convective model, and that was only capable of looking at global average temperature, but it looked at that temperature in multiple layers in the atmosphere, and that's what you see here. And in that simple model, Manabe and Weatherald increased levels of a powerful greenhouse gas, carbon dioxide, from 150 to 300 to 600 parts per million. And when they did that, they obtained an insight that nobody had obtained before, that you more effectively trapped heat lower down in the atmosphere, in the troposphere, when you increase CO2. The troposphere warmed, and the layer of the atmosphere above the troposphere, the stratosphere, cooled, in part because the lower atmosphere was more effective in trapping heat. And that cooling, as you can see here, was predicted to get larger the higher up you got above the Earth's surface. What you see there on the y-axis is the altitude in kilometers above the Earth's surface. The important thing here is this was a true prediction. This is 1967. We don't have the satellite data to determine whether this prediction is correct or not. We do have some weather balloons that measure atmospheric temperature back then, but they don't have the structural integrity to get above about 20 to 25 kilometers. They burst. So we really didn't know whether this predicted stratospheric cooling signal was real or not. It was real. So these are beautiful measurements from NOAA, National Oceanic and Atmospheric Administration, satellite-based microwave sounders. What do these instruments do? They look at the microwave emissions from oxygen molecules, and those emissions depend on the temperature of different layers of the atmosphere. By measuring at different microwave frequencies, you can literally back out the temperature of different broad layers of the atmosphere. And that's what you see here. And this is exactly Manabe's fingerprint. Cooling of the stratosphere, with cooling getting larger the higher up you go above the Earth's surface, and warming of the troposphere, with the largest warming over the Arctic, where Arctic sea ice extent has, over the last 46, 47 years, decreased by nearly 50%. So the data are in broad agreement with what Manabe and Weatherall predicted back in 1967. We also have, as I mentioned, as part of this consilience, pattern recognition methods. This gentleman here, who looks a little bit like Kenny Rogers, is Klaus Hasselmann. And one of the extraordinary privileges of my scientific career is that I was able to do my postdoc with Klaus Hasselmann at the Max Planck Institute for Meteorology in Hamburg. And at that time, Hasselmann had developed these pattern recognition methods to try and separate human and natural effects on climate. I'll give you an example of what I mean. So the bottom line in these methods is that different things that influence the climate have different characteristic signatures in temperature patterns, for example. And that's what you see here. The top panel shows a computer model calculation where you do a thought experiment and only change the sun's energy output according to our best understanding of how the sun actually changed. And again, what we're doing is we're looking through the atmosphere from the surface, in this case to 30 kilometers above the surface. And in climate model world, this is the fingerprint of the sun. And the yellow to orange colors there means that if we're understanding the sun's energy output correctly, we think it's slightly increased over the last 50, 60 years or so. That would lead to more sunlight arriving at the top of the atmosphere and warming throughout the full vertical extent of the atmosphere. The panel on the bottom was generated with the same climate model, but looks only at human-caused changes in carbon dioxide arising from fossil fuel burning. And that shows the very pattern predicted by Manabe and Weatherall, warming low down, cooling of the upper atmosphere. I won't get into the details, but the important take-home message here is these two things are different, and that was Hasselmann's insight. If we look at patterns, we have discriminatory power. We can try and separate the fingerprint of the sun, or the fingerprint of volcanoes, or the fingerprint of natural internal variability from the fingerprint of human-caused changes arising from greenhouse gases. And like Manabe, Professor Hasselmann won part of the 2021 Nobel Prize in Physics for this key insight that patterns can be useful in trying to understand the causes of climate change. I'm going to give you an example here of how we do fingerprinting in the real world. This is from a paper we published several years ago, and the bottom line conclusion from this paper is that if we looked at atmospheric temperature from the surface right up to 50 kilometers above the surface, where Manabe and Weatherall in 1967 had found this very large predicted signal of human effects on climate, we got this result. I'll just read it. Extending fingerprinting to the upper stratosphere with long temperature records and improved climate models means that it is now virtually impossible for natural causes to explain satellite-measured trends in the thermal structure of the Earth's atmosphere. Reaching that finding was a roughly 30-year odyssey for me. Our group published a number of different papers where we kicked the tires. We looked at the reliability of the climate models. We looked at the reliability of the data. we looked at the fingerprint methods. And I'll try and give you a flavor in non-mathematical form of what fingerprinting actually is. One of my postdocs, when I was still at Lawrence Livermore National Lab, taught me how to use matplotlib, which extended my scientific career by at least 5 or 6 years. And what I'm going to show you now was produced with matplotlib. So I'm going to show you satellite measurements of atmospheric temperature, like the ones I showed a few slides ago. And again, we're going to be looking through the atmosphere from the surface right to 50 kilometers above the surface. This is data, again, from these microwave sounders. And we're going to step through the data 3 years at a time. This is 1986. Again, for those of you who can't see it, the y-axis goes from about the surface to 50 kilometers above the surface, and the x-axis goes from the South Pole to the North Pole. 1989, 1992, 1995, 98, 2001. And what you can see over time here is that the data are showing the very thing that Manabe and Weatherall predicted: warming of the lower atmosphere and cooling of the upper atmosphere. It's there in the data, and it's coherent. By that I mean, when you look across latitudes, it's there at all latitudes. You can compare this sequence of observational patterns of climate change with a result from a climate model. This isn't only from one climate model, it's from 9 different state-of-the-art climate models in which you increase carbon dioxide and other heat-trapping greenhouse gases according to our best understanding of how these gases have actually changed. And you can compare that model predicted fingerprint, which again, as in the simple Manabe and Weatherall calculation, shows warming low down and cooling of the stratosphere. You can compare that fingerprint with the sequence of observations and calculate some statistic that measures the pattern similarity between the human influence fingerprint and the data. And that statistic shows you what your eyes tell you, that yes, over time the data are becoming more similar to the fingerprint. There are also a lot of interesting features here. For example, this dip here in pattern similarity is caused by a big volcano, the eruption of Mount Pinatubo in the Philippines in 1991. Pinatubo did the converse to the human influence fingerprint. It cooled the lower atmosphere and warmed the upper atmosphere. And that's why you see this dip here. This spike here is a big El Nino event, a natural warm event in 1997, 1998. So as climate scientists, we try not only to understand this overall increase in similarity between the data and the model human influence fingerprint, we also try and understand the wiggles, and we do. We understand many of the wiggles. So how might you as a scientist try and assess whether this increase over time in similarity between the model predicted human influence fingerprint and the data is unusual or not? Could it just be chance? Could it just be the vagaries of natural climate variability? Well, you look at that by doing these world without us simulations. So in climate model world, you can run models for thousands of years with no human-caused changes in greenhouse gases, and you get these kind of patterns here. I'm only going to show you a brief selection of these, stepping through 300 years at a time from 9 different climate models. And again, we're looking from the surface to 50 kilometers above the surface, and from the South Pole on the left to the North Pole on the right. And what you can see relative to what I showed you for the actual data is these patterns are much noisier. They show areas where temperature increases and decreases, but you don't see that warming of the lower atmosphere across all latitudes, or that cooling of the upper atmosphere across all latitudes. Again, you can compare these patterns of natural climate variability with the human influence fingerprint, look at some measure of pattern similarity, and I'm using the same y-axis scale here that I showed you when I compared the fingerprint with the data. Again, you can see sort of what your eyes tell you, that on 40-year timescales, which are those green trends here, there are periods where by chance the fingerprint agrees with natural fluctuations in climate, and that's what's encapsulated in this distribution of noise trends here. This is, in model world, what nature alone can do in terms of giving you pattern similarity with the fingerprint. And this is where we are in terms of comparing the fingerprint with the actual data from satellites. And this is this extraordinary difference between the comparison with the data, the red line, and the comparison between the fingerprint and natural climate variability is what enabled the statement that I read to you. It's virtually impossible, if model estimates of internal variability are realistic, and we can get back to that assumption later, to explain the observed result by natural variability. Why? Well, this is why. Again, on the left there, you see the human influence fingerprint from climate models, essentially all the world's climate models. And from the model control runs, you see in the middle and on the right estimates of natural climate variability in the vertical structure of atmospheric temperature. They're very different. The noise of natural climate variability is small scale. It shows features that we as climate scientists understand, anti-correlations between what's happening here at high latitudes and what's happening in the tropics, or anti-correlations between what's happening at the two poles. If you look at the blue over the South Pole and the red over the North Pole, nature doesn't look anything like the human influence fingerprint. This goes to show you that in every climate model we looked at, and there are 9 here, when you run it with increases in greenhouse gases, this canonical pattern of warming of the lower atmosphere and cooling of the upper atmosphere, with cooling getting larger the higher up you get into the stratosphere, it's there. There are differences between models, but the basic pattern is there in every model from Manabe onwards. And it's there in the satellite data too, as you can see in the panel on the bottom right. Recently, just last year, we performed a little thought experiment and asked, when could we have known? When could we, if we had had satellites back in 1860, have first identified a human signal on atmospheric temperature? The answer surprised us. Why did it surprise us? Because if you had started monitoring atmospheric temperature in 1860, the initial increase in carbon dioxide from 1860 through to 1900 is small. It's only 10 parts per million. That's 9 times smaller, nearly 10 times smaller, than the increase in CO2 from 2000 through to the present. So this is a very small signal, but even so, that small increase in CO2 in the upper stratosphere, which is what you see on the right, was already causing cooling. So these kind of ripples here that you see on roughly an 11-year timescale, that's the signature of the sun. The sun varies on roughly 11-year timescales. You can see the maximum solar output there indicated in those purple lines. The line that's indicated by Krakatoa, that's a big volcanic eruption in 1883 that had a profound influence on the temperature of the stratosphere. But the take-home message from this is that in model world, we likely could have identified a human effect on climate as early as the 1880s, before the advent of the gas-powered car. Because, again, as predicted by Manabe and Weatherald, the upper stratosphere is where a human-caused signal is very large and the noise of natural variability is very small. It's a really favorable place to look for human effects on climate, a canary in the coal mine, if you will. All right, getting back to the discernible human influence finding. That finding was finalized between November 27th to November 29th in the beautiful Palacio de Congresos de Madrid, with this wonderful Miro mural on the front. It's 3 days I'll never forget. That finding, as I mentioned, was extraordinary, and it led to a lot of consequences, I would say. I was investigated by Congress. The sources of my funding were investigated by Congressman Dana Rohrabacher. There were calls for my dismissal with prejudice from my position at Lawrence Livermore National Lab. It was rumored that I was going to be indicted by the Hague International Court of Justice for, quote, falsification of international relevant scientific documents. It was a bad time. Nothing in my training as a scientist had prepared me for that. You're prepared as a scientist to defend the work that you do, the appropriateness of the research methods, the appropriateness of the inferences that you draw from the data, from the models, from the methods that you apply. But you're not trained to defend your integrity in the public arena, how to fight back when, say, as in my case, the Wall Street Journal publishes an op-ed about you in which you're falsely accused of serious professional misconduct. How do you fight back? What lessons do you learn from that kind of experience? And that's what I'm going to speak a little bit about now, the lessons learned, at the end of my talk. One is defend scientific understanding. As I see it, there's no point in being a scientist if you're unwilling to defend the hard-won understanding that you and your colleagues have gained over decades. The second is never engage in science by eminence of position. What do I mean by that? Don't say, trust me, I'm a scientist at a national lab. Do the science necessary to address the criticism. Both of these things were really powerful lessons, because back in 1995, I didn't have the luxury of retreating to my office, closing the door, and hoping the bad stuff would go away. That wasn't a good strategy for responding to these concerted attacks on the IPCC, on the science of climate change, and on my own person. Another lesson learned that I'll also try and illustrate is find creative ways of using your voice. Sometimes it's not enough just to publish papers. We have to do other things, and I'll speak to you a little bit about that. And fourth, declare your values. This isn't just a science problem. This isn't just the science of fingerprinting. This is also about what kind of world we want to live in and what our values are as human beings. And I'll speak a little bit about that too. So these first two issues, defend scientific understanding and never engage in science by eminence of position. I'm going to give you a brief example, a very recent example, of what that looks like. This report came out in July of 2025. It was by the US Department of Energy, an official government report. It was not produced via an official process. Indeed, a judge ruled that the process by which this report had been generated was secretive and illegal, but the report is still up there on the Department of Energy website. I was deeply troubled by this because I worked for the Department of Energy at Lawrence Livermore National Lab for 30 years. We've spoken about the evidence from fingerprinting with atmospheric temperature. That evidence was directly addressed in the DOE report. Here's what the report said, and I'll read this. A combination of tropospheric warming and stratospheric cooling, which we just talked about from Manabe and Weatherald onwards, is a commonly cited fingerprint of anthropogenic climate change. Stratospheric warming since 2000 coincides with continued surface and tropospheric warming, a pattern that is not found in climate model simulations and is not apparently consistent with the anthropogenic fingerprint. In making this statement, the DOE report explicitly cited the paper that I showed you earlier, our 2023 paper that showed that there was a human fingerprint on climate. The only analogy I can give is looking outside the window and it's daylight and someone's trying to convince you that what you're seeing out there isn't actually day, it's night. That's the level of misrepresentation here. But rather than just saying that, my colleagues and I did additional science, which we published in the peer-reviewed literature, to show how this claim was wrong, how it was demonstrably false. So there is no stratospheric warming since 2000. Again, the blue here are the satellite measurements of stratospheric temperature change at 3 different levels from roughly 25 kilometers to 50 kilometers above the surface. The red line is at 2000 there. The green lines are natural events. So you see the warming in the stratosphere caused by the eruption of Mount Pinatubo in the Philippines. You see the extraordinary Australian wildfires, particularly there in that bottom panel, that happened around New Year's in 2019, 2020. Those fires were powerful enough to loft soot into the lower stratosphere, where they have a little signal there. And the other green line, Hunga Tonga, is the big submarine eruption in the Pacific of this underwater volcano that injected enormous quantities of water vapor into the upper atmosphere. The kicker here from this is that if you look at the very region where Manabe and Weatherall predicted we should see a large human-caused cooling signal, there is. It's there in the data, it's there in the models. Again, those undulations, those wiggles that you can see there in the data and the models, that's the roughly 11-year solar cycle that you're seeing here. So how could the DOE report make this claim that the stratosphere is warming? Well, it seems that they were focusing on this layer of the atmosphere, the lower stratosphere, about 15 to 20 kilometers above the Earth's surface. That's where most of the ozone is located. And from 2000 through to the present, there's been little or no warming in this layer, both in the models and in the data. So I'm just going to toggle back and forth. This is mid to upper stratosphere. This is lower stratosphere. And you can see that there's far less warming in the lower stratosphere over this period in both the models and in the data. Why? Well, the previous speaker in this series, Susan Solomon, found out why in this beautiful paper published in Science in 2016. What Susan showed was this. This is a key figure from the paper. It's a complex figure. Only look at the black dots. The black dots are measurements of the size of the ozone hole. And from 1980 through the end of the 20th century, you can see that the size of the ozone hole in September increased because our actions, producing chlorofluorocarbons, were destroying ozone in the lower stratosphere where most ozone resides. But because of a good thing that we did, the Montreal Protocol and its successor amendments and agreements, ozone started to recover in the early 21st century. And that's what you can see after 2000 there in the black dots, that the size of the ozone hole is decreasing because of what we did, because of the international agreements that the world put in place. So the lower stratosphere is a complex place where there was cooling up to about 2000 because of ozone depletion, and there's been some small warming afterwards due to the effects of the Montreal Protocol. And as you can see here, by comparing the black dots with, say, the red line there, models and observations concur just as they do here. So the DOE report was fundamentally misrepresenting this very complex science. And we pointed this out in a paper just published last month in AGU Advances, where we did this science in the peer-reviewed literature rather than trust me, I'm a bigwig scientist at a national lab. And we showed what I've just showed you, that human fingerprints marked by tropospheric warming and stratospheric cooling are evident in the data, and that a claim to the contrary in a recent report of the DOE is incorrect, and that indeed the fundamental issue raised by the DOE that models are not capable of capturing the observed temperature changes in the lower stratosphere in the early 21st century, that claim is verifiably false. So find creative ways of using your voice, just at the end here. If you're lucky, when you publish a scientific paper, you reach a couple of hundred people around the world. I've had the extraordinary opportunity to work with these two playwrights, Joe Murphy and Joe Robertson, on the play Kyoto that was recently performed at the Lincoln Center in New York after being performed at Stratford-on-Avon by the Royal Shakespeare Company and in London at the Soho Place Theatre. Kyoto, as its name suggests, is about the Kyoto Protocol in December 1997. The coming together of essentially all the countries in the world to recognize that, yes, human-caused warming is real, it's happening, and that recognition was partly due to the discernible human influence finding. And at Kyoto, the nations of the world agreed to do something about it. What I've described to you today, what happened in Madrid, the genesis of those 12 words, is part of the play. And I'm there on stage talking to myself. This gentleman is the actor who plays me in the play. It's an extraordinarily unsettling experience to be sitting next to yourself and to watch elements of your life that are very unhappy elements, like what happened after the discernible human influence finding, play out in a theater, but also, again, a way of reaching many, many thousands of people around the world that you couldn't hope to reach through your science alone. This BBC 4 radio play is also about how the discernible human influence finding came together and what happened after that. And it enabled me to meet my fiance. So talk about unintended consequences. There are other ways, creative ways of using your voice, going outside of your comfort zone as a scientist and writing for other non-peer-reviewed publications like the Bulletin of the Atomic Scientists or Scientific American, and writing not purely about the science alone, but about human values. What's important to you? This was perhaps the most terrifying creative way of using my voice, appearing on Late Night with Seth Meyers back in 2017. This was shortly after Senator Ted Cruz had appeared on Late Night with Seth Meyers and had made the incorrect claim that satellite data show no warming, no significant warming from 1997 through to the present. And my colleagues and I, again getting back to lesson 1 and 2, published 2 papers in the peer-reviewed literature showing that Senator Cruz's claim was wrong. Even if you did cherry picking, which is what he was doing, those claims were demonstrably wrong. And that led to this opportunity to restore balance to the force by appearing on Late Night with Seth Meyers, which I'm happy to talk about. It was truly terrifying. Declare your values. I'm not just a climate scientist. As I showed you at the beginning, I'm also a climber. I've been climbing around the world since I was 18 in beautiful, fragile, high alpine environments around the world. These are pictures that I've taken in the Alps, in the Himalayas, in the North Cascades, and most recently on the Juneau ice field in Alaska. Over one human lifetime, I've witnessed profound changes in these beautiful places. We're losing them. That discussion, what we lose when we lose glaciers, when my son no longer have the opportunity to stand on glaciers that I once stood, or to visit the Great Barrier Reef and see it in something like its present-day form, or to visit tropical rainforests, what does that mean? How does it diminish us as humans if we lose these places? What value, not monetary value, but value to who we are, what value do we all have for these beautiful, fragile places? This is Camp 18 on the Juneau Icefield. I've been privileged to do research there and to lecture to students since 2014. If you ever get a chance to go there, go. This is looking down onto the beautiful confluence of two glaciers. It's called the Gilkey Trench. That highway-like feature you see in the middle is a moraine, and the surface elevation here of the glacier has decreased by about 200 feet since 2000. The rate of change is absolutely extraordinary. Go see these places if you can. Figure out what they mean to you. Just finally, the other lesson I've learned is be brave. There are very powerful forces of unreason out there that seek to remove from you and from me the ability to do science, the ability to understand this beautiful and complex world and its climate system and how and why it's changing. Our ability to do that work is not an inalienable right. It's a privilege. And in my opinion, we need to fight to maintain that privilege. Thank you very much. Happy to answer any questions you might have.
And because we're being recorded, we have a mic in the center. I'd ask if you could use that. I know it's a little awkward, but.
Don't be shy. A large part of the reason I'm here is to interact with you and to find out what your concerns are at this extraordinary time and what it feels like to be in your shoes to try and do climate science and environmental science in these difficult times.
Thank you so much for being here. Hello.
It mostly works for the recording, probably won't be loud.
Well, thank you so much for being here. Kind of just my first question to hopefully get things started is, like, even from your experiences with like Late Night with Seth Meyers, or even, you know, perhaps outside of focused academic spaces, what are some, I guess, tools of the trader's rhetoric that you picked up in terms of sharing kind of the more scientific data focused on the stratosphere and whatnot into, in some ways, just colloquial speak, or just more communicable ways that people that don't have experience can understand? Thank you.
Thank you for that great question. And I'd like to tell you that there were courses that I took that prepared me for what I would encounter after the balance of evidence finding. It was on-the-job training. There were no courses in how to get a response published in the Wall Street Journal, how to distill complex science into plain English, how to speak in front of Congress, another terrifying kind of experience. And you learn by doing these things, and you try and get better. Every lecture is an opportunity to figure out what works and what doesn't work. And you learn about visual presentation too, how important that is. Fingerprinting is about patterns. You've got to be able to display those patterns and show this is the fingerprint of the sun, and it's different from our best understanding of the fingerprint of human influence. That's critically important, that visual presentation. And I hope that there are courses like that that prepare you for communicating with the public, both in written form, through presentations, and also visually as well. I wish those kind of resources had been available to me when I was a student. And again, It's on-the-job training. I'm trying to get better every time. The other thing I would say is that it's really helpful to look at every word on the page. Of course, we didn't have AI back in my day, and the challenge was to find the right words. That was the challenge in Madrid. How could complex scientific understanding encapsulated in hundreds of papers be distilled into those 12 words? And I would argue that's still the challenge today. Language is powerful. That's what I learned in Madrid. Words can change the world. How do you find the right words when you're writing a scientific paper, or when you're speaking to friends, or when you're trying to write a term paper? Every word matters. Think about the words carefully.
Hi, I'm Sarah Mitchell. I'm a geology professor here. I'll be having dinner with you later tonight. How do you maintain optimism, if you do maintain optimism, in sort of the political climate these days where a report like the one you just talked about comes out with just obvious falsehoods? The EPA stops saying that CO2 is a pollutant. These very political decisions are being done without science, essentially, or counter to our understanding. And how do we kind of keep going in a world like this?
Thank you for that question, and I'm looking forward to dinner tonight. These are tough times. What is that line in A Tale of Two Cities? It was the best of times, it was the worst of times. These are really bad times, but also there are extraordinary opportunities, even in these bad times, to speak science to power, to reach audiences using the mechanisms I mentioned, plays and art and TV and social media. How do we make the best use of those opportunities to tell people about the reality and seriousness of climate change? How do we convey to them the fierce urgency of now, that our decisions will matter for many, many generations, the decisions we take today about how to deal with this problem? So that's the way I try and look at it, that every lecture, like this one today, is an opportunity to throw that stone in the pond. You don't know what complex pattern of ripples is going to propagate out from that simple act of giving a lecture, throwing the stone in the pond. You just got to keep trying. And I'm profoundly grateful that you, through the education that you provide here for the students, are throwing a lot of stones in the pond, a lot of different ponds, and you have no idea what the consequences will be of giving understanding to the people in your care.
A bunch of my students are here right now. What did we just do in lab today? We threw stones in a pond today.
Those are good stones. More questions? Yes.
Hi. How do you have you ever encountered working with communities that aren't that easy to translate scientific terms or understanding things like that? Because when I think of my own family, my home language, it's Darim, which is a small country in Burma, ethnic group. And it's really hard for me to explain these climate issues and make people that I care about care, just because the language translation and also just the lack of knowledge is something that I find a huge barrier to communicating these issues.
Thank you for that great question. And I encountered that in Madrid back in 1995, because all the countries of the world, essentially, 96 different countries were present in Madrid. And what we understood was that those 12 words, the balance of evidence suggests a discernible human influence on global climate, would be translated into dozens of different languages. Would they have the same meaning in Chinese and French and German and in Russian? What would discernible mean in a different language? Was there even an equivalent word? All these nuances of language matter in talking to people, and I hope that the IPCC, the Intergovernmental Panel on Climate Change, is now devoting more resources to outreach and to figuring out that English can't be the only language by which we try and explain complex science to the rest of the world. It seems to me that that's so important to translate the guts of the science into terms that others can understand, and to learn from people who are not scientists. What's their experience, which is what we try and do in Alaska, to learn from Native Americans up there. How has your world changed over your lifetime and over generations? What's your experience of these changes in glaciers, what that means for flooding in communities like Juneau? It's got to be a two-way conversation. I guess that's a lesson I forgot to put up there, not just scientists handing down knowledge from on high. Does that make sense? More questions? Again, don't be shy.
Hi, thank you so much for coming. I was just kind of curious, so obviously our current administration that we have in America right now is doing a lot to repeal a lot of acts that are pretty foundational to both climate change, sustainability, in pretty much any way they can, like you mentioned, kind of disregarding science. So what do you kind of see how that's going to change in the future? What do you hope is going to change in the future? And do you see a way that America can kind of come back from what's been repealed and kind of changing that nature? And do you think it could happen?
Yes, I think it can happen. Again, these are tough times. A lot of decisions have been made that will have long-term consequences. For example, pulling the United States out of the Intergovernmental Panel on Climate Change and the Framework Convention on Climate Change and the Paris Climate Accords, decreasing funding for universities, making it less attractive for foreign students to study climate science or for US students to study climate science in this country. Those decisions will have long lifetimes. It's not like you can flip a switch and suddenly reverse those consequences. On the other hand, I do believe that it's possible to reach people irrespective of their political affiliation or any other kind of affiliation, because this is all we've got. We're not Elon Musk. We're not going to go to Mars. This pale blue dot, as Carl Sagan referred to, is all we have. And we've got to figure out how to live on it harmoniously and with a relatively stable climate system. And the decisions we're taking now, particularly here in the United States, are dangerously destabilizing the climate that you're going to experience, that you're going to grow up in, that your kids are going to grow up in. No, that's inherently unfair to burden you with an environmental debt that you did nothing to generate. So it's incumbent on our generation to do everything that we can in order to change that narrative and to point out what's at stake. What is the likely climatic shape of things to come if we embrace willful ignorance with open arms and say, no, that's not daylight outside, it's night? Those consequences are serious, and I do believe that, again, people, irrespective of their political affiliation, ultimately care about the world that they're going to leave behind for their kids and grandkids. And that's the challenge, to have those kind of conversations where we talk about our shared human values. That's what I want, those kind of conversations, like this one today.
It could be a great place to end, unless someone has another good question.
I'm happy to answer more questions if you have them, but let me know. I'm also, Keith knows my email address. I'm happy for him to share that with you if you have any follow-up questions.
Thank you very much.
Thank you, Tom.